Hello everybody, today's video is section 3.3, types of statements. The first type of statement we're going to talk about is a tautology. So a tautology is a compound statement that is always true, regardless of the truth values of the simple statements that make it up. So for example, I am going to Palm Springs for spring break this year, or I'm not going to Palm Springs for spring break this year. Well, if I do go to Palm Springs for spring break, then this would be true. But also, if I don't go to Palm Springs for spring break, this would be true because I said I was going to do either or. So no matter what, this statement is always true. Kind of the opposite of that is our second type of statement, which is called a self-contradiction. So a self-contradiction is a compound statement that is always false. For example, I'm going to Palm Springs for spring break this year, and I'm not going to Palm Springs for spring break this year. Well, I don't think it's possible for me to go to Palm Springs and not go to Palm Springs at the same time, so this statement will always be false. All right, let's look at exercise 1. So we have two simple statements. The first P is I'm going to an outdoor concert, and the second Q is I will wear a denim jacket. For each statement below, first write the statement in words and try to predict if the statement is a tautology, self-contradiction, or neither. So is it always true? Is it always false? Or is it a combination of true and false? All right, and we can check whether or not it's always true or always false by making a truth table. So let's just look at part A. So part A here, we have this disjunction or this or, and we also have an if-then. So this is saying if P or Q, then Q. So if we were going to write this in words, what we would have is if I'm going to an outdoor concert, or I'll wear a denim jacket, then I'll wear a denim jacket. Okay, so when I look at that sentence, I don't immediately know if this is always true or always false. Like I talked about in class, sometimes these sentences that we come up with for our truth tables don't sound super correct to us. So it's not very obvious here. So I think we're going to need to use a truth table to figure out if this is a tautology, a self-contradiction, or if it's neither, and it could be true sometimes and false sometimes. All right, so looking back at the symbols we need for part A, we have a P, we have a Q, we don't have any negations, but I have a disjunction and I have a conditional. So in my table, I'm going to need a P, I'm going to need a Q, I'm going to need the disjunction, and then I'm going to need the conditional. Okay? So let's start with our normal setup. So we either have both true, one true and one false and one true, or both false. Now we want to look at the disjunction of P and Q, or the or statement. So in the first one I have P is true, Q is true, so are either or of them true? Yes. In the second one, P is true, Q is false, but at least one of them is true, so my or is true. Similarly for case 3, at least one of them is true, so the or is true. But in case 4, they're both false, neither of them are true, so my or would be false. Now I'm doing my conditional, and I'm doing a conditional from my disjunction to Q. So remember, we kind of talked about this in class. I'm going to look at this column, and I'm going to do my conditional going in this direction. So we kind of have to read our table backwards with our rules that we talked about in our last video. So if P or Q, then Q. P or Q is true, Q is true, so my premise happens, the conclusion I wanted happens, so this is true. If P or Q, then Q. My premise happens because it's true, but my conclusion did not happen. So remember, for if-thens, this is the only case where we would have false. Again, we have true to true. And then in the last one, we have false to false. But remember, when we start with the false, it means our premise didn't happen. So we don't know what the conclusion is going to be, so this could be true. Okay, so when I look at my last column, which is the column that we care about, right? The one that we were looking for. Let me erase what I highlighted here. Now we're just looking at our last column for our answer. And these are not all true or all false. So this is neither a tautology nor a self-contradiction. So again, they're not all true. They're not all false. So this would be neither a tautology nor a self-contradiction. What we have in part B is P and Q and not P and not Q. So let's translate this and see what that would say. So remember, P says, I'm going to an outdoor concert, and Q says, I'll wear a denim jacket. So what this statement says is, I'm going to an outdoor concert, and I'll wear a denim jacket. And I'm not going to an outdoor concert, and I won't wear a denim jacket. Okay, so when I read this sentence, it kind of sounds like a self-contradiction because it says, I am going to the concert and I'll wear this jacket. And at the same time, I'm not going to the concert and I won't wear the jacket. So it's very similar to that Palm Springs example we had where like, how can you do both at the same time when they're complete opposites? So if I had to guess, I would say this is a self-contradiction. So if you want, why don't you pause the video and try to fill out this truth table, or at least pause it for a few seconds and see if you can get the headings right. So which parts you would need to make this last column be this entire statement. All right, so take a second and try that on your own. Okay, hopefully you paused it and you tried. So now when I look at this statement up here, I see that I have a P and a Q, which we always start with. But when I look in the second half, I also see that we have a not P, and I see that we have a not Q. So now I have all of like the basic parts that I'm going to need when I use my connectives. So I also have a conjunction with my normal P and Q, as well as a conjunction with my not P and not Q. And now, since I have my first conjunction and my second conjunction, I can make my large conjunction. So I have P and Q and not P and not Q. All right, let's use our rules to fill out this table. So again, we have our starting cases where they're both true, one's true, one's false, one's false, one's true, they're both false. Now we're going to jump into our negation. So remember, all you need to do is write the opposite truth value. So looking at the P column, I used to have true, so not P would be false. Again, I had true, so now I have false. When P was false, not P will be true. Similarly for not Q, when Q was true, not Q will be false. When Q was false, not Q will be true, and I'll just continue that pattern. Now I want to go back to looking at my normal P and Q, and I want to apply the rule for a conjunction. So remember, ands are only true when they are both true. So in this first case where I have T and T, that's where my conjunction will be true. Everything else has only one truth or no truths, so everything else here is going to be false. Do the same thing for my not P and not Q. In my first case, I have two falses, so the and would be false. In the next two cases, at least one of them is false, and only in my bottom case are they both true. Now in my very last column, I'm going to be comparing this fifth column with this sixth column, and again I'm doing an and statement. So on the top I have true and true. Just kidding, I have true and false. So for my and, this is going to be false. Then I have false and false, so again, that's still false. Remember, the only time an and is true is if they're both true. My next one again is false and false, and my last one is false and true, which is still false. So like we suspected, our last column are all false. So this would be a self-contradiction. All right, hopefully that makes sense. If not, you can definitely watch me go through that table again. All right, let's move on to logically equivalent. So, two compound statements are logically equivalent if and only if they have the same truth table values. The symbol that we use for logically equivalent is kind of like an equal sign with an extra line, so it has 3 lines. Okay, so logically equivalent does not mean tautology or self-contradiction only. It just means that the truth table values at the end match. So they don't have to all be trues or all be falses, but we'll be comparing two separate statements, and we want their final truth values to be the same, to match each other. So let's look at this first one. So we have a conditional, if P then Q, and then we also have this disjunction, so not P or Q. And what we're going to do is we're just going to use one truth table to compare these two different statements. And how we do that is we basically just want the last two columns to be the two statements we're talking about. So I want to end up with one of my statements here and my other statement here. And at the end, I'm going to compare these two columns to see if the values match. Now, in order to figure out the truth values for these two statements, I see that I'm going to need a P and I'm going to need a Q. And the only other piece I'm going to need is a not P. So again, let's set up our table with our basic setup of all the cases. Now let's look at not P. Again, you just need to put the opposite truth value of P. Moving on to our fourth column, we have an if-then statement, and I'm going from P to Q. So just like our, woo! So just like our normal one, I'm going from P to Q. So let's apply the rule for the conditional. So if they're both true, it's true. True to false is the only time it's false, and the other two cases are true. And in our last one, we have not P or Q. So I'm looking at these two guys together. So if one of them is true for an or statement, then the whole thing is true. So since Q is true, I'm good. In the second one, both Q and not P are false, so I'm still false. In the next one, our third one, they're both true. And in the last one, the not P is true, so we're good. So now when I look at these last two columns, I see that their truth tables match. So let me erase all the other stuff I wrote, and we're just going to look at these guys. This one goes true, false, true, true. This one goes true, false, true, true. So since their truth values match, these are logically equivalent. So our truth values match. Since both statements are identical, we have that these two statements are logically equivalent. All right, let's look at exercise 2. Determine if the two statements not P, then Q, and if not Q, then P are logically equivalent. Now I already set up the beginning of this table for you, so with the headings. So why don't you again pause the video and try to fill out this table in your packet and see if the last two columns match. All right, so hopefully you paused it. Let's try this one together. Again, I have my basic setup. My not P, I'm going to do the opposite of P. My not Q, I'm going to do the opposite of Q. And now I'm going to do my conditional. So for the first one, I'm going from not P to Q. So I'm reading backwards. So I have false to true, that's still true. False to false is still true. True to true is true, but true to false is false. All right, and then for our last one, we are going from not Q all the way to P. So I'm kind of ignoring the things in the middle and I'm reading backwards this way. All right, make sure you're really reading your charts in the correct direction. They don't always go from left to right. Okay, so if not Q, then P, I have false to true, that's true. True to true, that's true. False to false, that's true. And true to false is false. So hopefully you found this when you did it yourself, that again, these tables match at the end, right? Our last two columns are exactly the same. So these two statements are logically equivalent. Okay, so keep in mind the differences. We have a tautology, which means the last column will be all T's. We have a self-contradiction, which means the last column will be all F's. And then we have logically equivalent, which just means the two statements you're comparing at the end of their truth table have matching rows. Okay? Now, this one that we just did, we can show in words why this might be logically equivalent. So I'm just going to write down an example. So let's say that P, this is not in your packet, by the way. Let's say that P says John's salary is above the poverty line. And we'll let Q say John qualifies for food stamps. Okay, so then our statement which was not P, then Q, would say, if John, let's fix that, if John's salary, let's count the typos in this video. If John's salary is not above the poverty line, that would be not P, then John qualifies for food stamps. Okay, that would be our first statement. Our second one, which is our not Q, oops, wow, okay, then P, this would say, if John does not qualify for food stamps, then John's salary is above the poverty line. So maybe saying this in words kind of shows that these two statements are basically saying the same thing, that these statements are logically equivalent. First one says if it's not above the poverty line, then he can qualify for food stamps, versus if he doesn't qualify for food stamps, then he is above the poverty line. So just an example in words to hopefully show that these two statements do basically say the exact same thing. All right, De Morgan's laws for logic. Now, in your packet, there's kind of a typo, and it's also in your textbook written incorrectly, so I highlighted here the part that's wrong. So De Morgan's laws for logic should say, for any statements P and Q, the negation of the statement P or Q. So we're in our packet, we're missing negation of the. So again, the negation of the statement P or Q is logically equivalent to not P and not Q. And similarly, we're missing this again. The negation of the statement P and Q is logically equivalent to not P or not Q. So fix that in your packet. Sorry again that it's incorrect. All right, so what that's saying in symbols is if I negate P or Q, this will be logically equivalent to not P and not Q. Again, that's that symbol for logically equivalent. And the second statement says if I negate P and Q, this will be logically equivalent to not P or not Q. Now, hopefully you recognize the word De Morgan because we've actually used De Morgan's laws already when we were studying sets in the last chapter, right? And we had complements. So here, think of the negation kind of as like the complement, because remember it means opposite, just like complement means like what's left outside. So if I take the complement of the union, or if I take the negation of the or, I end up with the intersection of the complements, or I end up with the and of the negations. Similarly, if I take the complement of the intersection, I end up with the union of the complements. Just like here, if I take the negation of the and, I end up with the ors of the negations. So we normally use De Morgan's laws to write negations of conjunctions and disjunctions, or of ands and ors. For example, the negation of I will go to work or I will go to the beach is I will not go to work and I will not go to the beach. So notice I added nots to each statement and the or became an and. So when you negate a conjunction, it becomes a disjunction. Or when you negate an and, it becomes an or. And when you negate a disjunction, it becomes a conjunction. In other words, when you negate an or, it becomes an and. let's try to do that with some of our statements. So write the negation of the following statements using De Morgan's laws. Studying is necessary, and I am a hard worker. Well, basically, I need to throw the word not in here a few times, and I need to change and to or. If I wanted to write this in symbols, I could think of it as P being studying is necessary, and I can think of Q as I am a hard worker. So what I currently see up there is P and Q. But what we're asked to do is to write the negation using De Morgan's law. So I want to negate this statement, which according to De Morgan's law would be logically equivalent to not P or not Q. So if I translate that, I'm going to have studying is not necessary, or I am not a hard worker. All right, let's try the next one. So shoplifting is a felony or a misdemeanor. All right, so I'm going to think of shoplifting as a felony as P, and I'm going to think of shoplifting is a misdemeanor as Q. So right now what I have is P or Q, and if I negate this, it should be logically equivalent to not P and not Q. In words, I have shoplifting is not a felony and is not a misdemeanor. All right, part C is kind of cool. If you want, you can try it on your own for a second and then come back and see how you did. So what I need to do for part C is first let's identify what we want to be P and Q. But notice when I read this, there's actually three statements. So the patient needs an RN or an LPN, and she's very sick. So the patient needs an RN will be our P. Maybe I'll type it out again. So we'll have P say the patient needs an RN. I'll let Q say the patient needs an LPN. And I'll let R say she is very sick. Ignore the fact that the P and Q got capitalized. Okay, so what I have right now is P or Q and R. Do we see that? So this is the patient needs an RN or the patient needs an LPN and she's very sick. But this little disjunction happens first. So if I want to apply De Morgan's law to this, let me rewrite it down here. I need to negate the whole thing. So I'm going to put in these big brackets, like order of operations, and I'm going to negate. We're first looking at the fact that this is an and statement. Okay, so according to De Morgan, the and becomes an or, and the first part gets negated and the second part gets negated. So I'm going to have the negation of my first part, my and will become an or, and then the negation of my second part. But notice that I can apply De Morgan's law again to figure out what this is going to be, because this is the negation of an or, right? And the negation of an or, according to De Morgan's law, is an and, where the first and second part are negated. So I'm going to write that part in red to show that it's just what I have highlighted. So this is going to be not P and not Q. And then I haven't changed anything about the second part, which was my or not R. So we had to use De Morgan's law twice. And this red part was like our first section. So in words, the negation would say, the patient does not need an RN. Let me make that bold like I did before. Does not need an RN and does not need an LPN, or she is not very sick. Let me go back and italicize the connective. All right, so that's a pretty cool one because we actually had to do it more than once. You can apply De Morgan's law over and over and over again if you have to. Hopefully you don't have to, because it could probably get a little confusing. But I tried to highlight to show like which part was changing each time, so hopefully that helped a little bit. All right, the negation of a conditional. So using De Morgan's law, we can find the negation of the conditional. Earlier, we established that if P then Q was logically equivalent to not P or Q. So if you forgot where we did that, we actually did it in a truth table. This one. Remember, we showed that if P then Q was logically equivalent to not P or Q. Okay, so that's the fact that we're stealing right now. Okay, so what we want to do is we want to look at what we have here. And what I did was I just negated each side of this. So notice if I just, put parentheses around this and I negate the left side and I negate the right side, I end up with what I have written right here. So it didn't come out of nowhere. It's just showing that I can negate both sides of my equation. Think about like when you solve an equation, if you add something to one side, you have to add it to the other. So if you negate one side of an equation here, you got to negate one side of an equation. Or think if you negate one side of a logically equivalent statement, you should negate the other side of the logically equivalent statement. So now looking at these two, we want to use De Morgan's law on the right-hand side. So we're using it on this piece here. So looking at this guy, that's what I have down here. All right, so if I apply De Morgan's law, this or is going to become an and I need to negate each piece inside. So really, it's like I have not P and not Q, but this not, think of it like going away, so it's just going to leave P like I have here. So therefore, now I can jump back to the beginning, which is what I had here. This was logically equivalent to this not that we applied De Morgan's law on. So this thing I have highlighted in pink will be logically equivalent to what I have down here. So I can just rewrite it as one statement, that the negation of the conditional of P and Q is logically equivalent to the conjunction of P and not Q. If that was confusing, feel free to watch it a few more times or write it out on your own paper. It might help if you actually go through the process of, distributing the negative and then realizing that this piece here is just this piece here. So if I just ignore what I have here, these two things will be left being equal. Because if you want to see it let me just add a little bit. If I get rid of some of the stuff I drew, I can say now, as I saw below, that this is logically equivalent to what I have here. Right? So now if I just remove the middle part, since all of it's logically equivalent, then that means this first pink part should be logically equivalent to this black part, which is what I have written down here. Okay? All right, so let's try to show this using a truth table. So in this truth table, I need to make sure I have all the pieces from those two statements. So I have a P, I have a Q. I do not have a not P. I have a not conditional and a normal P, so I don't need a not P, but I do have a not Q, so I'm going to need one of those. Then I'm going to need to know what this conditional statement is, as well as this and statement. So next thing I'm going to do is write down the conditional. Then I can find the negation of the conditional. And lastly, I can find the conjunction of P and not Q. And then I can just see if these last two columns actually do match in my truth table to show that it's logically equivalent. Okay, if you want, try it on your own. I'm probably just going to cut part of this out and have the answer pop up. So take a second, try it on your own, and then come back. Okay, so hopefully you got this for your table. So if you look at the last two columns, we do see that they're the same, so these are logically equivalent. Great. So here's an example in words. Write the negation of the statement. If you agree to go out with me, I'll buy you a laptop. So we'll let P be you agree to go out with me, and Q, we'll say I buy you a laptop. So the statement if P then Q can be negated as P and not Q, right? So you go back up to your truth table, we saw that if I take the negation of P and Q, if P then Q, I get the exact same equivalency as P and not Q. So I'm going to negate this statement using the fact that it's the same as P and not Q. Well, P is you agree to go out with me, and not Q is I do not buy you a laptop. So the negation of the statement up here, if you agree to go out with me, I'll buy you a laptop, is you agree to go out with me and I do not buy you a laptop. So now we know a few different negations. We know the negation of the and, right? I can just use De Morgan's law to show that the equivalent negation is not P or not Q. I also know the negation of or. Again, I can use De Morgan's law to show that the negation of the or is not P and not Q. And then we just showed from that truth table that the negation of the conditional is the same as P and not Q. All right, some variations of the conditional. Remember, conditionals are if-then statement. So, from the conditional statement, if P then Q, three other related statements can be formed. They're called the converse, the inverse, and the contrapositive. So symbolically, what these would look like is our original statement is our conditional. So if P, then Q with the arrow. The converse of the conditional is just flipped around. So if Q, then P. The inverse of the conditional is not P, then not Q. And the contrapositive of the conditional is really just like the flipped version of the inverse. So if not Q, then not P. So here's an example in words of what the converse, inverse, and contrapositive would look like. So let's say our original conditional statement is, if you earned a bachelor's degree, then you got a high-paying job. So for us, P is you earned a bachelor's degree, and Q is you got a high-paying job. Or remember the converse, we kind of need to flip it. So the converse would say, you got a high-paying job, then you earned a bachelor's degree. The inverse is if not P, then not Q. So if you did not earn a bachelor's degree, then you did not get a high-paying job. And the contrapositive is kind of flipped of the inverse. So if you did not get a high-paying job, then you did not earn a bachelor's degree. All right, guys, I hope that was helpful for section 3.3. Again, I really recommend that you do pause the video when I ask you to and try it on your own, since we don't have that time in class anymore to like work with each other. It'll at least give you some idea if you are comprehending what I'm talking about. Good job today, or at least for this video. Our next video will be 3.4. See you then.